So the first lesson in this unit deals with working with radicals. That's the name of the section in your textbook. It's section 5.1. A lot of this is a very quick review of grade 10 math. Let me get that other monitor going. I thought I turned it on. There, it's going to be on in a second. A lot of it is a quick review of grade 10 math. But we build on that very quickly to turn it into something more complicated. And we're going to be working with what are called mixed radicals and entire radicals. And you should be able to convert from mixed radicals to entire radicals and entire radicals to mixed radicals. And then we're going to do one more thing that you didn't talk about in grade 10 math, which is how do you add or subtract radicals. So to begin with, and this is a review from grade 10, convert all of the following entire radicals to mixed radicals, and we've actually done a lot of this in the previous unit. When we had the quadratic formula in use, we would have the square root of b squared minus 4ac, and we would very frequently convert it to a simpler form. The idea here, and we're going to talk about a couple of ways to do this, okay? And you're coming from a whole bunch of different Math 10C teachers, so you have different ways to do this, but we're going to focus on a couple. The first method is the preferred method for me when we're dealing with square root radicals, not necessarily when we're dealing with cube root or fourth root or fifth root, but if we're dealing with square root radicals, all I'm interested in is two numbers which multiply to give the radicand. That 44 is called the radicand. So I'm not going to write this every time, but now that I've introduced you to that word, in case you've forgotten it in grade 10, from grade 10, hopefully I'll just be able to say the radicand is 44 and you'll know what I'm talking about. We're looking for a product of two factors for the radicand, one of which is a perfect square. Your perfect squares are 1 squared, which is 1. That's a useless piece of information because 1 is a factor of everything. But 2 squared, which is 4, 3 squared, which is 9, 16, 25, all of those numbers that are perfect squares. And the reason is, and this is what you learned last year in grade 10, you learned that when you multiply two radicals together, you can multiply the radicands together. So I'm using this property of math that says the square root of one number times the square root of another number is the square root of the product of those numbers. But I'm just working backwards here. I'm saying, and I don't know, I think you probably have had a math teacher in the past, many of you in grade 10, that did this, and then they wrote root 4 times root 11. I don't think we need to write root of 4 times 11 and then break it apart. We can just break it apart. And this becomes then 2 root 11, because the square root of 4 is 2. So think of I know that this is a really simple question, but it's going to get more complicated in a short period of time. And I often will see students, please don't write this down, but I often will see students do something like this. They'll go root 4, root 11, and then they'll go, well, the square root of 4 is 2, so I have root 2 root 11, which is root 22. In fact, that happened last week somewhere, I think. We were doing a question and somebody had done that. What's the problem with what this person has done? Who can tell me? Yeah.
You've already square rooted the 4, so like the 2 is just 2 answers.
Right. I like what you said. You've already square rooted the 4, so you don't have the square root anymore, right? It's just 2. And the point I want to make is, so this is just 2 root 11. Think of this symbol that I'm about to highlight as an instruction. It's telling you to take the square root of what's underneath it. And once you've followed the instruction, you don't have the instruction anymore. I don't, when I'm making cheesecake, I don't go to my recipe and it says cream 3 packages of cream cheese, and I cream them, and I look at my recipe book and it says, oh, cream 3 packages, and I repeat it, right? I've followed that instruction, I move on to the next thing. It's fairly obvious to some people, but later on you'll find yourself doing that when it gets more complicated. The answer is 2 root 11, that's it. Any questions with A. All right, B, root 48. So what you want to do is find a perfect square that divides into 48. I'm going to give you a second, and then I'm going to ask somebody for a perfect square that divides into 48. Ashira, do you have one? 16. Wow. And that's good, because what Ashira has given me is the largest perfect square, which is ideal. That's what we want to do. 16 divides into 48 3 times. And you know, I think you should know some basic math facts, but there's nothing wrong with you using your calculator, plunking around on it, and finding numbers that work. And the square root of 16 is exactly equal to 4, so this is 4 root 3. And before I go on, I really want to impress on you what this means. If you look at the square root of 48, and by the way, I know this is being picky, but it's an academic math course. That number that's on my calculator is not the square root of 48. Because the square root of 48 is an irrational number. It has decimals that go on forever. That number that's on my calculator is a decimal approximation of the square root of 48. Right? It's irrational. If you try to convert it to a fraction, no go. When we say simplified, it's 4 root 3, we simply mean that 4 multiplied by the square root of 3 will give you the same decimal approximation. It's the same number, we just can't see all of the decimals. Now, I want to go back over here to this one. No, I don't want to do that yet. How many of you, when I said I'm going to ask you for a perfect square that divides into 48, thought of the number 4? There has to be somebody. That's your immediate reaction. 48 is divisible by 4. 40 is divisible by 4. 8 is divisible by 4. So here's a mistake that you can make. You go, okay, I can break 48 into 4 times 12. That makes sense, yes? The square root of 4 is 2, so this is 2 root 12. All right, I'm going to pack up and go home. No, because what you're going to have to do all the time in this part of this unit is anytime you think you're done, look at any radicals that are there and ask yourself if you can do it again. Is there a number that divides into 12? 4 again. So this 2 is just coming along for the ride. It's part of the number. And then I can write root 12 as root 4 root 3. This becomes 2 times 2 because the square root of 4 is 2 times root 3. I didn't say this explicitly, but there is always multiplication occurring between these pieces. And what we get is 2 times 2, which is 4, times root 3. So now I want to do one other thing. Well, let's do the third one, and then we'll do the other thing. The cube root, actually I better not do that. I want to go back to this one, A. Did anybody have a Math 10 teacher that said, what we are going to do is take 44 and write it as all of the factors of the prime numbers? Meaning, you take 44 and you say, well, that's 4 times 11. Better yet, that's 2 times 22. Would you agree? And then you go, that's 2 times 2 times 11. Is this ringing a bell, I hope? And that means that root 44 is the square root of 2 times 2 times 11. And then you can see what the perfect square is. 2 times 2 is the perfect square. So we end up having the square root of 2 times 2 times the square root of 11. And the square root of 2 times 2 is 2. Okay? I want to make this point here, and it may be obvious right now, but it's going to become less obvious later, that root A is A. Whether I write root of A times A, or root of a times root of a, it's a. And this is the point. Since we're dealing with a square root, there is a pair of 2's that can be extracted and written as a single 2 outside. Okay, so what would happen here with this one is you would say root 48. Well, let's see, 48 is 2 times 24, which is 2 times 6 times 4, which is 2 times 2 times 3 times 2 times 2. So what I'm dealing with, and this is not what I would recommend for square roots, but it's going to be important that you understand this process in a minute. That means that this root 48 that we were trying to simplify is the square root of 2 times 2 times 3 times 2 times 2. And it's a square root, so we're thinking pairs. Is there a pair of numbers that are equal? Yes, this pair of 2 2's. So I can obliterate those 2 2's underneath the radical and write a single 2 outside, because the square root of 2 times 2 is 2. So in my next step, I can put a single 2 outside that comes from these 2 2's inside of the radical, and I can put another 2 outside that comes from this pair of 2's inside of the radical, and I'm left with 3. So you get 4 root 3. Are you guys with me on this? Okay. Are you in agreement that this is maybe more work than it needs to be for square roots? Okay. But here's why it's easier to do it the other way. We're able to come up with perfect squares in our head pretty quickly. Okay. If you look now at C, cube root of 400 means if you do it the simple way for square roots, then your job is to come up with 2 numbers that multiply to give 400, one of which is not a perfect square, it's a perfect cube. Now, I'm just curious, how many of you know of a perfect cube that divides into 400? Not as many people, right, as if I were to ask about perfect squares. The perfect cube is 8. But until you do more work with exponents and get more comfortable with some of these numbers, you will not recognize cube roots. 8 is a perfect cube. 27 is a perfect cube. 64, 125, like some of you may know them, but you may not. So what we do instead, we don't do this. We break 400 up into as many factors as we can. And this is not a Math 20 idea. You know, you might start off with, I would do this. I don't like going 2 all the time because it just seems like a real chippy process. Take out a 2, take out a 2, take out a 2. I try to find some bigger numbers. So the 10 is 2 times 5. The 40 is 5 times 8. And 8 is 2 times 2 times 2. And guess what I'm suggesting to you is I don't think this should be a big deal. I think you ought to be able to break down a number like 400 into all of its prime factors. Do me a favor and just make sure that this is correct. If I multiply 5 times 2 times 5 times 2 times 2 times 2, does it give me 400? Yep. Okay. So that means the cube root of 400 is the cube root of 2 times 2 times 2 times 5 times 2 times 5. This is almost just scrap paper work. I think we can go from here to the answer, but I'm going to rewrite this as the cube root of 2 times 2 times 2 times the cube root of 5 times 2 times 5. And I want to make this point. the square root of a times a is just a. We can try this. What's the square root of 3 times 3? Well, 3 times 3 is 9. What's the square root of 9? 3. It's like a cheesy magic trick. What's the square root of 11 times 11? Well, 11 times 11 is 121. What's the square root of 121? Surprise, surprise, it's 11. Okay. The same thing is true for any root. When you take a radicand that has a factor that occurs n times, and you take the nth root, you're going to get a. You're going to get that radicand base. So, for example, this is the cube root of 2 cubed. I don't think most of us need to write this down, but we might as well multiply this out. This is 50. Figure out what 2 cubed is, and then take the cube root of it. So if you were to do that on your calculator, you would go 2 cubed, and then you would take the cube root of that. You can go to your math menu and go cube root of the 8. You get 2. You shouldn't need to do that, because by definition, the cube root of a number is the number that you cube to get that number. So the cube root of 8 is 2 because 2 cubed is 8. So this becomes 2 cube root 50. And what I'm going to recommend that we do instead of this long, complicated process is once you get all of the factors written, like I have them at the top of the screen, you're simply going to look at what's called the index of the radical, and then you're going to find groupings that occur that many times. So if it's a cube root with an index of 3, you're looking for a triplet. You're not looking for a pair, you're looking for a triplet. And if you have 3 2's, then you can extract that 3 2's out of the cube root and put it as a single 2 inside. This is not what you would do for square roots because it's too much work. Convert all of the following mixed radicals to entire radicals. Well, if when you have something squared under a square root, it's simply raised to the 1 outside, that means if I want to put it back inside, it has to be squared. So, again, I'm showing an awful lot of work here. I don't think we need to do this, but 5 is the square root of 5 squared. These two things are the same things. And now I have 2 radicals, and if I want to put them together as an entire radical, I can take that 25 times 13. You can get 325, I think. Thank you, Nate. The square root of 325. Most of the time we go from an entire radical to a mixed radical, but there may be occasions where we want to go the other way. All right, so what if we had 3 root 2? Well, that's root 9, root 2, which is root 18. And I didn't write root 9 times 2 this time. I just wrote root 9 times root 2 and said I have to multiply the 9 and the 2 because they're both radicands. Still good? Okay, so when you take a number that's outside of a radical and you put it in the radical, you raise it to the exponent of the radical's index. So when we took the 3 and put it inside, we squared it because the index of this radical is a 2. It's a square root. Well, that means if we're going to put 4 inside of a cube root, we have to cube the 4. Another way to look at this is if you have 3 4's under a cube root, that's the same as 1 4 outside of the cube root. So putting this all together, whatever 4 times 4 times 4 times 16 is, $836? No? 384. Boy, I was way off. 384. So this is the cube root of 384. Don't know what I was doing to get whatever I said. Another 2? Oh, I see. Okay. That's the answer. Okay, let's get to some examples. That was just warm up, and quite frankly, you probably did some of the cube root stuff last year. There's something that's significantly different in these examples, and that's that there's variables involved. Express each entire radical as a mixed radical in simplest form. Before we do, we're going to do a mini lesson here. I would like everybody to take the square root on your calculator of 12. I want a decimal approximation. And you don't need to write this down. I'm going to write this down up here. If you feel at some point you should write this down, then go ahead. But this is going to be a number between 3 and 4, because 3 squared is 9 and 4 squared is 16. Charlie, what do you get?
3.46.
3.46. Can I just say about 3.46? Okay. Go ahead and take the square root of negative 12. Well, I hope many of you just say I can't. But that's not possible. This doesn't exist. It's just, you can't do it. Why? That's a good question. Why can you not take the square root of a negative?
Because square roots are like perfect squares, or when you multiply a number by itself. And so if you have two negatives, they become a positive, so you can't really take a square root.
Right. And I'm going to paraphrase that a bit for everybody. The square root of something is the thing that squares to become the thing you took the square root of. So this 3.46 approximately is the thing that when you square it, it will give you 12. So this thing that we're trying to find when we talk about the square root of negative 12 is apparently going to be a number that when you square that number, which means you multiply it by itself, will give you negative 12. But when you multiply a number by itself, you will never get a negative. You will get a positive. Okay? So you cannot take the square root of a negative. You can take the square root of 0. Okay, I would like you to take the cube root on your calculator of 12. And I'm going to go out on a limb and say it's in between 2 and 3, but Charlie, you're my helper here. What are we going to get for the cube root of 12?
10.39. Or 10.39. Maybe did I do it wrong?
So cube root of 12. How we do this is we go to the math menu, choose cube root, and then 12. Whoops. Don't know what happened there. Go to the math menu, choose cube root of 12. I'm getting 2 point. Are you okay with it now? Yeah. Okay. So I'm getting about 2.29-ish. What about the cube root? There's nothing special about the number 12, by the way. It's just a number that popped into my head. What about the cube root of negative 12? Can we do that? Well, let's find out. How many of you are convinced you can? Because the cube root of a number is going to be the number that you cube to get what you're taking the cube root of. That's confusing. So it's a number that if you multiply it by itself 3 times, you'll get negative 12. Well, a negative times itself 3 times will give you a negative, because negative times negative times negative will give you positive times negative, which gives you negative. So this exists, and probably not a big surprise. It's negative 2.29-ish, right? So you can take the square root, you can take the roots of negative numbers sometimes. And you can not take, you're not allowed to take the roots at other times. As a general rule, when can we take the root of a negative?
When the index is odd number.
Right, when the index is an odd number. So third roots, cube roots, fifth roots, seventh roots, ninth roots. You can take those roots of positive or negative. But you are not allowed to take even roots of negative radicals. Okay? So, now let's go to this question. The question says we have to simplify this, but let's do the restrictions on the values for the variables first. These is going to be what we call non-permissible values. Is there a value for f that's not allowed here? No, there's no value that's not allowed, because it doesn't matter what f is. You're taking the cube root of something. So when you take the cube root of something that's positive or negative or zero, you're allowed to. So there are no restrictions here. Because even if f is a negative number, you're going to be taking the cube root of a negative number. So let's simplify this. And many of you are going to be able to do this very quickly without doing all of these steps. I'm going to break 120 down into all of the prime factors. And you're going to do the same thing. So take a minute on paper and figure out what 120 is when you break it down into all of the prime factors. I start at 12 and 10, because I can break down 12 pretty quickly and 10 pretty quickly. I believe 120 is 2 times 2 times 3 times 2 times 5. And this is the part that you're not going to like doing, so you want to try to get a way around it. F to the 5 means f times f times f times f times f. So since it's a cube root, we are looking for items that occur as a group of 3 factors. I have 3 2's and I have 3 f's, so I can extract those 3 2's as a single 2 because the cube root of 2 times 2 times 2 is just 2. And the cube root of f times f times f is just f. And then we're left with, I call them the leftovers. Whatever you have left over, pack it back together. So I have 3 times 5, which is 15, f squared. I'm hoping that many of you will appreciate that if I had the cube root of 2 times 2 times 3 times 5 times 2, and then I also have f to the 5, I hope you understand that there are 5 f's, so you can take 3 out and have 2 left over. And if this were f to the 10, you could take out an f and an f and an f and be left with 1 f inside. Because you're taking out a group of 3 out of 10, that leaves you with 7. You're taking out another group of 3 out of 10, that leaves you with 4. You take out a third group of 3, that leaves you with 1. Okay? Are there restrictions here? Well, yes, m must be greater than or equal to 0, because if m is negative, m to the 7 will be negative, and you cannot take the 4th root of a negative. 4th root all of a sudden, out of nowhere. So if this were a square root, you'd be looking at what's a perfect square. Finding perfect 4s is not easy. So we're going to break this down. Take a minute with your calculator or your brain, figure out how you can express 32 as a product of really tiny numbers, which we call primes. Have you got it?
It's just 2 times 5, like 5 twos.
5 twos, 2 to the 5. We could even write this. I'm going to put 2 to the 5 on the side. Okay, we could do that. I'm going to do it this way though for everybody. 2 times 2 times 2 times 2 times 2. And then I'm going to put m to the 7. I really don't want to have to write m times m times m times m times m times m times m. So it's a degree 4 index, right? It's an index of 4. So we are looking at a group of 4. There's 4 twos, so I can take that and write it as a 2 outside. And without writing out m to the 7, I hope you understand there's a group of 4 m's in m to the 7. And when I say a group of 4 m's, I mean m times m times m times m. So I can bring out a single m outside and be left with the 4th root of, what do I have left? I have a 2, and I have m cubed. Now, do you see how I'm forcing you to think of the m to the 7 as containing 4 m's, and it's going to become m to the 3 when you extract those 4 out? We could do the same thing here. Do you see there are 4 twos inside of 2 to the 5? There's a group of 4, so put a single 2 outside, and you will have left 2 to the 1. And you take out 4 m's, and you have m cubed. In either case, it's 2m, 4th root of 2m cubed. Let's try another one. Oh, back to a square root. Does yours have a square root here? Okay. So I might be inclined here to just do this. If you want to write 3 times 3 times 7, feel free. But it's 9 times 7 is 63, and the square root of 9 is 3, so it's going to go outside. And I also have, for this one, I am going to write this out. N. I'm not really enjoying myself, but the fact that I'm not enjoying myself tells me it's not something I want to do all the time. And then p to the 4. And I'm hoping that in doing this example, by writing it out, it will reinforce to you how you can do it without writing it out. The 9 outside of the square root is going to become a 3. I'm going to take out pairs of n's. So each of those pairs of n's becomes a single n outside, which is n cubed. I can take out a pair of p's and a pair of p's and write it as a p times a p outside, which is p squared, and simply have root 7n. Other than the numerical part of this, I hope everybody sees why the p to the 4 is obliterated inside and just becomes p squared outside. Because there's an even number of groups of p's. Well, there's 2 groups of p's. And if I have 7 items and I want to compartmentalize them in groups of 2, I have 3 groups of 2 with a leftover 1. Any questions with that example? Any restrictions? Is there a restriction on n? N is not allowed to be negative. N must be greater than or equal to 0. Otherwise, you'll have the square root of a negative. Is there a restriction on p? There is not a restriction on p. Why is there not a restriction on p? So the lesson is just because it's a square root doesn't mean there's a restriction on everything. But why can p be a negative number? Craig?
Since its exponent is even, it will never end up being negative.
Right. Since the exponent on the variable p is an even number, that would make it negative before you take the square root. So anytime you have an even exponent on a variable, one other thing to remember, you don't have to worry about a restriction. Let's move on. Convert each mixed to an entire radical. Well, this just means since it's a square root, the 4 inside will be squared and the x inside will be squared. So again, when you have something here, you square root it. But if you have something outside and you put it in, you square it. There's a difference between squaring and square rooting. So now we simplify this and get 48 x cubed for a radicand. Are we asked about restrictions here for this set of examples, or it just says simplify? Just simplify? You know, don't be surprised if on an exam it says simplify, comma, x is greater than or equal to 0. It's just telling you there's a restriction, but it's not important in the work. J to the 4 cube root j. Because what I have to do here is I have to take underneath that cube root, I have to put j to the 4 3 times, don't I? I'm going to break this down and explain it in a little more detail in a second. I apologize for missing that 4. So what we end up with is the cube root of j to the 4 times j to the 4 times j to the 4 times j to the 1. And you're taught that when you have a product of powers that have the same base, you add the exponents. That goes back to grade 9. There is another way we could have done it. Instead of writing the cube root of j to the 4 times j to the 4 times j to the 4, we could have written the cube root of j to the 4 cubed. Do you agree that j to the 4 times j to the 4 times j to the 4 is j to the 4 cubed? Okay. Times another j to the 1 in terms of a cube root. Does anybody remember what you do with these exponents when you have, we call this a power of a power? You multiply. 4 times 3 is 12, plus that other one will give you 13. So this is the answer to the question. Since it's an odd root, you can have j being anything. 2k times the 4th root of 4k. I missed that exponent again. I just said 2k, and it's 2k squared. 2k squared outside of a 4th root is going to be 2k squared times 2k squared times 2k squared times 2k squared inside of the 4th root, and then we have 4k. I'm going to leave a space here because I'm going to show you an alternate way we could write that. But before I do, we simplify this and you get the 4th root. Let's see, k squared times k squared times k squared times k squared is k to the 8 times that other k to the 1 is k to the 9. And then I have 2 times 2 times 2 times 2, which you can work out to be 16. Are we okay with that? Yeah.
What does it mean when it says state the values of the variable for which the radical is a real number?
It just means state the values for the variables that are allowed, or state the values that are not allowed. So when we said earlier, and by the way, in this particular question, it's an even root. So if you were asked for the allowable values, you would say k is greater than or equal to 0. And asking for the allowable values could be worded many ways. State the values for the variable that produce real numbers is a way of saying what is the variable allowed to be. Yeah.
Wouldn't it be 64?
Oh, did I miss my 4?
Yeah.
Yeah, 2 times 2 times 2 times 2 times 4. Thank you. 64. Got to pay more attention here. Okay. I'm warming you up to Math 30 here, that rather than writing 2k squared times 2k squared times 2k squared times 2k squared, why can't we just write 2k squared raised to the 4 in brackets? And if we simplify that, I'm just going to do this on the side here. 2k squared raised to the 4, we have to raise the 2 to the 4, and we have to raise the k squared to the 4. So you get 2 to the 4, which is 16. K squared to the 4, you multiply the exponents, you get k to the 8. And then you can multiply as well by the 4 and the k to the 1. You can feel free to take shortcuts here. There's not a lot of work to be shown. Simplify if possible. Okay. So this is the new part of the lesson, and it's the final part of the lesson. What do you get if I had $7 in this pocket, $3 in this pocket, and I add that $7 and the $3 together, what do I get? $10. This is why when you have 7x plus 3x, I will often say we're adding 7x's and 3x's. That's what this means. 7x is this. And you're going to add 3x's, which is this. The fact that what's after the coefficients is the same means we think about adding those things together. 7 chihuahuas plus 3 chihuahuas is 10 chihuahuas. So if you have 7 root 5s, I mean, I know you guys get this, I'm pretty sure. But if you have 7 root 5, you have 1, 2, 3, 4, 5, 6, 7 of these, and you're going to be adding 3 of these. I hope you don't have to count those things to see there are 10 of them. Right? Are you with me on that? Okay, it's 10 root 5. So this is what we call in math similar or like terms. Can we take 8 root 14 and subtract 17 root 14? 18 rather. Yes, because there are like terms. There are 18 root 14s, and we're subtracting 17 root 14s away from them, which gives us 1 root 14, and you certainly do not need to write the 1. So can we take 4 root 7 and add 5 root 10? No. We can do it on our calculator and get an approximate number, but me asking you to simplify this is no different than saying, I mean, I could really have fun if I were teaching a grade 8 or 9 math class and say, okay, everybody, I'll give you a minute. I want you to figure out what this is equal to. And then just walk away and just snicker to myself. Because it's not equal to anything other than 5x plus 7y. Those are different things. It's like adding cheeseburgers and kittens. If I have 4 cheeseburgers and 5 kittens, then I have 4 cheeseburgers and 5 kittens. There's nothing I can do. You know? And then all of a sudden I have 3 cheeseburgers because I've eaten one. Okay? There's nothing you can do with this. So is there anything we can do with this? Are you sure?
Can you simplify the radical?
Right, let's simplify these radicals. And this is kind of going to tidy everything up into a neat package. Because 4 root 18, well, root 18 is root 9, root 2. I believe since it's only a square root, we don't have to worry about writing out all the prime factors. And root 8 is root 4 root 2. Again, I just want to make sure that you understand this, that I'm doing this because these two things are perfect squares. So I get 4 times 3 times root 2 minus 2 times root 2. Remember that square root of 9 simply becomes 3 without a square root. 4 times 3 is 12, root 2 minus 2 root 2. We're going to talk more about this tomorrow, but the fact that the 4 and the 3 are both outside means we can multiply them together. It's no different than having 4 times 3x. You get 12x. Now, can I subtract them? Sure, I get 10 root 2 because now they're the same. Any questions with that one? All right. Root 18 plus root 32. Well, I don't want to push anybody here, and I do want you to understand that there's a level of an amount of work that needs to be shown. But I think in going from root 18 to 3 root 2 is not a difficult process. I'm not saying do everything in your head, but I'm saying sooner or later you'll become more familiar with some of these. Because root 18 is root 9, root 2. Plus, well, 32, how many of you see that 32 is 4 root 2? And the reason for that is 32 is 16 times 2. So root 32 is root 16 times root 2, which is 4 root 2. So 3 root 2 plus 4 root 2 is 7 root 2. Easy. Any questions with that one? Ooh, boy. Well, what we're trying to add here, everybody, is one of these, and we're trying to subtract from it 5 of these. These two things are as different to each other as cheeseburgers and kittens. They're not the same. We cannot take those two things and combine them. So we're going to simplify this. I'm just throwing this out here, and then I will explain why. By a show of hands, how many of you are okay with the fact that the square root of 4 times c cubed will be 2 times c times the square root of c? The reason is, there's a lot of different ways we can explain this. It's the square root of 4 times the square root of c times c times c, but it's a square root, so you extract pairs. And I have a pair of c's inside that I remove, leaving the one lone c inside. And those two c's that go out end up turning into 1, because the square root of this is simply c. The square root of c times c is c. Okay, minus, 5, and the square root of 9 is 3, and the square root of c cubed is c root c. So for the same reason, let me write it out here. I have 5 times root 9 times c under a square root. So I can take out 2 of those c's, write it as a single c outside, and the square root of 9 is 3. So now what I have is 2 c root c minus 15 c root c. And I would recommend to you that what you do is not think of these as being cheeseburgers and cheeseburgers. Think of them as being cheeseburgers and cheeseburgers. It's not that we're subtracting root c's, we're subtracting c root c's. I have 2 c root c's, and I'm taking away 15 of them. $2 minus $15 is negative $13. So I get negative 13 C root C's. The complexity of the problems grows, of course. This is just more work. I would like everybody to take a minute and simplify root 98. I'm not going to ask you to simplify root 10 because it doesn't simplify. Simplify root 8. Write it as a mixed radical in simplest form. And simplify root 40. So it's these three things that I'm going to highlight that you need to write in simplest form as a mixed radical. I mean, the better you are with your math facts, like 49 is a perfect square, and 25 is a perfect square, and 4 is a perfect square, the easier it will go. The root 98, I'm not going to write the 2 in here. The root 98 is root 49, root 2. The root 8 is root 4, root 2. The root 40 is root 4, root 10. So the square root of 49 is 7, the square root of 4 is 2, the square root of 4 is 2, and that's what we have. So putting this together, I get 14 root 2 plus root 10 minus 10 root 2 minus 6 root 10. So I have some root 2's and root 10's that I can bring together. 14 root 2 minus 10 root 2 is 4 root 2. We in agreement on that part of it? Then I have 1 root 10 minus 6 root 10, which is minus 5 root 10. Good? All right. One more. I think the final example just extends it into the realm of cube roots. We cannot combine these together just yet. But we can take 16 and figure out that it's 2 to the 4. So what I'm doing is I'm saying it's 2 times 2 times 2 times 2. 16 is 4 times 4. And each of those 4s is 2 times 2. So it's 2 to the 4. And in the next step, well, I'll ask the question again. How many of you see that it will turn into a single 2 outside and 1 2 left over inside? Those of you that see that, are you actually thinking inside that there's 2 times 2 times 2 times 2 and you're pulling 3 out? Okay. Is anybody thinking that I'm just going to subtract 3 from the exponent? And if I could subtract another 3, then I'd do it again and have a second C outside. And then plus, what do we have? 5. You got to figure out what 54 is equal to. And in my mind, this is my thought process. That's me. 54 I know is 9 times 6. As soon as I know it's 9 times 6, I can write it all out. It's 3 times 3 times 3 times 2. So it's 3 to the 3 times 2. And I have a group of 3's that can go outside and join forces with the 5. Well, that's nice. I'm left with cube root 2's, which is what the other term was. So I end up having 2 cube root 2 plus 15 cube root 2, which means I have 17 cube root 2's. And that's the answer. It's a whole nother level of arithmetic. I wouldn't really call this algebra because there's not much in terms, thank you for that, in terms of, variables in any of this. This should be 17. I probably said 17 and wrote 15. There's not much in terms of algebra, but there's arithmetic. There's numerical math involved in this. And you're going to find yourself, even though the basic ideas are pretty simple, you're going to find yourself going along and stumbling from time to time. I don't mean stumbling like doing that Mr. Way absent-minded thing where I write down the wrong number, where you'll use a square root twice, or you'll forget to use a square root. I've also seen this happen, by the way. I've seen people go from this, and when you see it, you'll go, oh, I would never do that. Well, don't say never. I see this a lot. And hopefully your eyebrows crinkle together and you go, well, why? I would never do that. But you might. You might just, in the heat of the math moment, go, oh, okay, now I've got a 49 outside. You have to take the square root of that. It becomes 7 root 2, not 49 root 2. Anyway, that's it. I seem to be a little off kilter today, but on page 275, 1 to 5 and 8 to 10 is the basic practice for your assignment. And then there's some extra stuff if you feel the need for extra practice. You can go to page 304 and it's questions 1 to 5.